Hello, and welcome back for another session in General Chemistry 2 from yours truly, Group Helium. If you remember, prior to this discussion, we addressed and resolved many cases involving stoichiometry solutions. This video will cover a range of topics, including word problems of colligative properties of solutions, vapor pressure, boiling point, freezing point depression, and osmosis. With everything that had been said, let's get to work and learn something new.
For the first problem that we have, the question is, the vapor pressure of pure water at 115 degrees Celsius is 1085 torr. A solution of ethylene glycol and water has a vapor pressure of 1.30 atm at the same temperature. What is the mole fraction of ethylene glycol in the solution? So, the given in this situation is that the vapor pressure of water and the solution of ethylene glycol together with water is 1085 torr and 1.30 ppm, respectively, and both have the same temperature of 115 degrees Celsius. Now, let's calculate for the mole fraction of ethylene glycol. First step is that we must convert 1.30 atm to torr so that both vapor pressures would have the same unit. According to the computation provided, 1.30 atm is multiplied to 760 torr over 1 atm, which would get a result of 988 torr. Second step is to determine the mole fraction of water wherein the vapor pressure of the solution is divided with the vapor pressure of water. Mathematically speaking, 988 torr is divided to 1085 torr, that would equal to 0.91 torr. Following Raoult's law, partial pressure of the solvent vapor above the solution is equal to the product of the mole fraction of the solvent and the vapor pressure of the pure solvent. Additional information is that the sum of the mole fractions must be equal to 1, thus X sub solvent plus X sub solute should equal to 1. Applying that concept, the equation would be 0.91 torr plus X sub Ag equals 1. Then 0.91 torr would be moved to the right. So for this problem, the mole fraction of ethylene glycol in the solution is 0.09.
Next problem states that what is the molality of a solution dissolved in chloroform that boils at 62.8 degrees Celsius when the boiling point of chloroform is 62.2 degrees Celsius and the molar boiling point constant of chloroform is 3.63 degrees Celsius per mole. Again, the identified given is that the solution dissolved in chloroform is at 62.8 degrees Celsius. T sub B is equal to 62.2 degrees Celsius and K sub B is 3.63 degrees Celsius per mole. Now, let's calculate for the molality of a solution. First, we should get the difference of the boiling point of solution and the boiling point of chloroform, which is 62.8 degrees Celsius minus 62.2 degrees Celsius, that will equal to the answer of 0.6 degrees Celsius. Applying the concept of boiling point of elevation, which is equal to the product of molar boiling point elevation constant times the molality of solution. When the formula is rearranged, M will be equal to 0.6 degrees Celsius divided by 3.63 degrees Celsius per mole. The final answer is that the molality of the solution dissolved in chloroform that boils at 62.8 degrees Celsius is approximately 0.17 moles.
Calculate the vapor pressure lowering dT when 10.0 ml of glycerol is added to 500 ml of water at 50 degrees Celsius. At this temperature, the vapor pressure of pure water is 92.5 torr and its density is 0.988 grams per millimeter. The density of glycerol is 1.26 grams per millimeter. Listed on the screen are the following given information for us to solve for the vapor pressure lowering. In order to solve for the final answer, the formula that we should be using is that P sub solution is equal to the product of X sub H2O times P sub H2O. But first, we need to calculate for the molarity of glycerol and water. For the molarity of glycerol, 10 ml of C3H8O3 times 1.26 grams per millimeter times 1 mole over 92.094 grams, wherein the 92.094 grams is the molar mass of glycerol, which would result to 0.137 moles of C3H8O3. Following the same procedure for water, we would get the result of 27.422 moles of H2O. Now, applying the concept, X sub H2O is equal to the molarity of water divided by the sum of the molarity of water and glycerol, which would result to 0.995. For the final step to solve for the vapor pressure lowering or dP, X sub H2O would be multiplied to P sub H2O, wherein 0.995 times 92.5 torr would result to 92.0375. The answer here is that the vapor pressure lowering dP is approximately 92.04 torr. For the final step to solve for the vapor pressure lowering or dP, the formula is P equals P sub H2O, which is 92.5 torr, minus P solution, which is 92.04 torr. The final answer we have computed is that the vapor pressure lowering or dP is 0.46 torr.
Example number 4 states that you add 1 kilogram of ethylene glycol under freeze to your car radiator, which contains 4,450 grams of water. What are the boiling and freezing points of the resulting solution? Here lies a given in this situation for us to find the boiling and freezing points needed to be calculated. First is to get the molarity of C2H6O2, wherein 1,000 grams of ethylene glycol is multiplied to 1 mole over 62.07 grams, which is the molar mass of C2H6O2, would equal to 16.1 moles of ethylene glycol. Now, to solve for the molality, the mole of solute is divided to the 1 kilogram of solvent, so 16.1 moles of C2H6O2 divided by 4,450 kilograms of H2O, which we just converted from grams to kilograms based on a given, is equal to 3.62 moles. So to solve the boiling point, the molar boiling point elevation constant 0.51 degrees Celsius per moles times the molality 3.62 moles will equal to 1.85 degrees Celsius. On the other hand, for the freezing point, the molar freezing point depression constant 1.86 degrees Celsius over moles is multiplied to the molality 3.62 moles. That will lead us 6.73 degrees Celsius. Final answer is that for the boiling point of the solution, after adding 100 degrees Celsius, the boiling point in the solution is 101.85 degrees Celsius, while the freezing point is negative 6.73 degrees Celsius.
The boiling point of an aqueous solution is 102.5 degrees Celsius. What is the freezing point of the solution? Let's start off by listing out the given in order to solve for the freezing point of the solution. First step is to get the difference between the boiling point of solvent and the boiling point of the solution, which we will have an answer of 2.5 degrees Celsius. Then, we would use the formula of T sub B is equal to K sub B multiplied by M to get the molality. Rearranging the formula and substituting the variables, the molality for the solution would be 4.88 M. Same as for the boiling point, we would use the formula of T sub F is equal to K sub F times 2M to solve for the freezing point of the solution. So 1.86 degrees Celsius times 4.88 M would equal to 9.0768 degrees Celsius or approximately 9.08 degrees Celsius. Last step is we need to solve for the difference of the freezing point of pure solvent and our calculated T sub F. Therefore, the freezing point of the aqueous solution is negative 9.08 degrees Celsius.
A solution of propylene glycol or an anion freeze in car's radiator has a freezing point of negative 20 degrees Celsius. What is the molality of the solution? So we would assume that the solvent is water so that we could provide a molar freezing point depression constant of 1.86 degrees Celsius over M and a freezing point of pure solvent of 0 degrees Celsius. To get the total freezing point of a solution, we will minus the freezing point of pure solvent to the freezing point of solution, so 0 degrees Celsius minus negative 20 degrees Celsius will equal to 20 degrees Celsius. Following the formula of T sub F is equal to K sub F times M, then rearranging it to M is equal to T sub F over K sub F for us to get the value of molality. Substituting the values, 20 degrees Celsius divided by 1.86 degrees Celsius over M, therefore the molality of the solution is approximately 10.75 m. Converting molality to molarity, we will assume that there is 1 kilogram of water, which is our solvent. So in getting the total mass of C3H8O2, we will multiply 10.735 m by 76.095 grams per mole to get 818.25 grams of propylene glycol. Then to get the total grams of C3H8O2, 1,000 grams of water is added to 818.25 grams of propylene glycol. That will result to 1,818.25 grams of C3H8O2. Converting grams to millimeter, we will get 1.75507 liters. Finally, to get the molarity, 10.753 moles of solute will be divided by 1.75507 liters. Therefore, the molarity of the solution is approximately 6.3 m of C3H8O2.
A solution prepared from 0.3 grams of an unknown non-volatile solute and 30 grams carbon tetrachloride has a boiling point of 0.392 degrees Celsius higher than that pure carbon tetrachloride. What is the molecular weight of the solute? Again, here are the given information for us to start solving for the molecular weight of the solute. First step is to find the value of m using the formula of T sub b is equal to K sub b times m. Rearranging and substituting the values, we would be able to get an answer of 0.078 m or mole solute over kg solvent. Then we need to convert the kilogram solvent to mole solute, so 0.03 kilogram solvent is multiplied to 0.078 mole solute over 1 kilogram solvent, and we would get 0.00234 moles of solute. Final step is to find the value of the molecular weight. M is equal to mass over moles, so substituting the values, 0.3 grams is divided to 0.00234 moles. The final answer that we have solved is that the molecular weight of the solute is 128.21 grams per mole.
Calculate the boiling point of an aqueous solution that contains 20 mass percentage of ethylene glycol or C2H6O2, a non-volatile liquid. After listing out the given, we need to find the molar mass of ethylene glycol, which is 62.07 or approximately 62 grams per mole. Then, like the previous problems, we will be using the formula of T sub B is equal to K sub B times M, and rearranging it for us to solve the molality of the solute. So M is equal to 20 grams of C2H6O2 times 1 mole over 62 grams, canceling out the same units, we will get 0.322 moles of ethylene glycol. The remaining 80% or 80 grams of the mass of the solution will be used to calculate the kilogram of the solvent. So 80 grams of H2O is multiplied to 1 kilogram over 1,000 grams to get a result of 0.08 kilograms of water. To get the overall molality of the solution, 0.322 moles of ethylene glycol is divided by 0.08 kilograms of water. That will get us an answer of 4.025 moles. Using the formula of T sub B is equal to K sub B times M, multiplying 0.1512 degrees Celsius over M by 4.025 m, the answer we will get is 2.0608 degrees Celsius. Then we need to add 100 degrees Celsius, therefore the boiling point of this aqueous solution is 102.0608, or approximately 102 degrees Celsius.
So this ends our discussion for today. We have learned a lot today, right guys? Next week, we will tackle about thermodynamics, so stay tuned for that. Once again, we are the group Helium, serving you with knowledgeable information that is necessary for general chemistry too. See you again next week for another session with us. Till next time!